Okay, take your attendances. Okay, class. So let's see. Continue. Okay, so I think we are still haven't complete the photoelectric effect yet. Okay, we are I think almost done. So we'll be just completing the discussion about the photoelectric effect. Okay, so recall back. So we go back to the slide. Okay, so what did you learn about quantum physics so far? First, we learned about photon, so packet of energy of an EM radiation, which dependent on frequency, right? And we talk about the controversial photoelectric emission electron halfway. Okay, we haven't reached the other two. Okay, so what is photoelectric emission? The release of what do you call? The release of electron from metal surface, and EM radiation is exposed to the metal. Okay. Okay, yeah, so we learned this formula. Then we talk about what is EM radiation. Okay, the release of electron surface of a metal, and EM radiation is incident on its surface. Then I told there is lots of controversial observation has been found. We need to know three. The emission is found to be instantaneous. Wave theory predicted should have a delay. Existence of threshold frequency to release the electron. Wave predicted any frequency should release the electron. Okay. The what do you call the emission of electron is independent of intensity but dependent on frequency. Okay. Wave theory predicted the other way around. Release of electron is dependent to intensity. And you can add another one. The different metal needs a different threshold frequency. Actually, all the metal can release electron. It should not have any threshold frequency. Yeah. Okay, then we talk about what Einstein told. So HF is the work function plus kinetic energy of the electron. Okay, then the Millikan help Einstein to prove the idea. Okay, so this graph is the work function versus frequency. Okay, sometimes some year they instead of stopping potential they put kinetic energy. They can put kinetic energy. Okay, so if they put kinetic energy versus frequency, kinetic energy versus frequency, huh? Okay, if they put yeah, kinetic energy versus frequency, then the gradient represents what? Kinetic energy versus frequency. The gradient will be what? The gradient will be a Planck constant, right? I think variety of type of graphs appears here. Kinetic versus frequency, stopping potential. There is one here, Bayesian. I go to the whiteboard. So HF equals to work function plus EVS or EV naught. Okay, EVS, EV naught. We serialize it. Okay. So yeah, sometimes EK plus work function is HF, right? So EK. So if you plot EK versus frequency, EK versus frequency is the easiest graph, right? Y equals to mx plus c. So your gradient is your h, your c is your y-intercept. So you got the same graph. EK versus what? EK versus frequency. So you get a straight line, and you get a y-intercept. Y-intercept is the work function. It's a work function. Okay. This will be something called the threshold frequency. The cutting is the threshold frequency. Okay, this is your threshold frequency. Okay, yeah, the graph. Okay, let me check. Am I recording? Yeah, it's recording. Okay. Okay, so yeah, more explanation. The collector plate negative, so that when the photoelectron move towards this one explaining is how to find the kinetic energy. I already told you this in last class, right? The half m squared, the EV is the half m squared. EV is the work done by the electric field. Is the kinetic energy possessed by the electron. Okay, so Millikan find the stopping potential. Okay, so and he work out the kinetic energy. Okay, so the current flowing through a circuit measured with a microammeter and the potential difference between the ammeter and the collector measured with a voltmeter. Yeah, the voltage between the ammeter and collector plates is gradually increased until the current drops to zero. The minimum value of potential difference necessary to stop the electron is called stopping potential. Yeah, so we got the kinetic energy. Okay. Okay, before we go to this, I need to tell something. Yeah. Where is it? Okay. Please include this in your notes. What is that? Is just now HF equals to work function plus EK, right? Okay. Actually, this EK labeled as EK max. It's labeled as EK max. Okay. Okay. So it's not only EK, it's just EK max. The question asks, why max? Why is max? Why EK max? Okay. So why max is, when the EM radiation shine on the plate, okay, the electron, of course, HF equals work function EK, all electron get same packet of energy. So HF is same, all of them getting, let's say 10 eV means all getting 10 eV packet. But the work function, right, okay, the work function, the bonding, some electron, the surface electron, the surface electron which are close to the surface because it's got full of atom, right? The electron at the surface, okay, will have its own kinetic energy. Okay, but sometimes the photon received by the inner shell electron, the electron which is kept inside the metal plate. Okay, so if the electron is inside, when he receives the HF, he still get the same HF, but because the electron is inside the metal plate, he needs some energy to come to the surface. Need some energy. Let's say this is the surface. Inner electron need some energy to come to the surface first before it was released. Okay. So what happened? Let's say you have one electron at surface 1, you have second electron deep inside, okay, and both getting the same HF, both getting the same packet of energy, but the E1 easily can come out. It will have one EK. So actually the work function, right? The work function stated here is the work function for the surface electron. The inner electron, uh, the energy required to release from the surface is greater. Okay, so all the electron, the E1 and E2, I will say E1 have a greater kinetic energy than the E2. The kinetic energy of the E1 is greater than the kinetic energy of the E2. So the electron actually, when released from the metal surface, the electron will have a range of energy actually. The range of kinetic energy. They will have a range of kinetic energy. The electron which is from the surface will have a high kinetic energy. The initial electron, the electron from the inner surface, will has a less kinetic energy. But you know, Millikan is technique used to stop the how you got the kinetic energy, how you got the stopping potential when the circuit current becomes zero, right? The current tend to become zero, right? Okay, let's say 100 electron released forward responsible for the original current before the voltage we make it negative, before we make the voltage become negative. Okay, no voltage yet. So let's say 100 electron causes the current, you got a certain current. But when you rise the voltage, when you make it negative, okay, when you make it negative, the current, that day I show you, the current will start to slows down. The current start to slows down, right? Slowly, not immediately drop to zero, right? You see here, this is the current. Okay, let's say I increase the voltage, you see, -2. You see the current here. This is the current here. I increase, see, current is slowly dropping. 1.442 become 1.08. You see, why the current not immediately drop to zero? Because the electron has a range of kinetic energy. The one slower kinetic energy, the one from the inner shell, from inner electron, when they come to the surface, they have small kinetic energy. They will be stopped first. The most highest kinetic energy will still contribute to the current. But Millikan adjusts this until current perfectly becomes zero, you know. So that means finally, the voltage he found is the voltage of the kinetic energy of the electron, which possess the highest kinetic energy, maximum kinetic energy, right? The hero, the last one who are so like Usain Bolt, the last highest kinetic energy guy will be stopped, then the current becomes zero. So Millikan only able to find the maximum kinetic energy. Yes, maximum energy. That's why in the equation, the EK normally labeled as EK max. We put it as EK max. Okay. So HF work function EK max. So in exam, they'll ask 2 marks question. Why EK max? Why EK is max? So you have to explain the story I told you. You have said the electron from the inner shell, the electron from the inner shell need more energy to be released, okay, from the surface. Okay, electron from the inner shell need more energy required to be released from the surface compared to the electron at the surface. Okay, therefore electron has a range of kinetic energy. They have a range of kinetic energy. Okay, so Millikan only able to find the EK max. Okay, the kinetic energy possessed by the most the greatest kinetic energy. So you need to justify that electron has a range of kinetic energy. Millikan only able to find the kinetic energy of the maximum kinetic energy only. Okay, that's why it's stated as EK max. Okay, put in your notes. The electron has a range of kinetic energy because the initial electron need more energy to be needed to be released before it was released from the surface. Okay, Millikan only able to find the EK max. Okay, so let's proceed. Okay, this slide. Okay, so explanation. Let me try to understand this. Okay, look at the first one. If F or lambda of radiation is kept constant, increasing the intensity of the radiation does not change maximum kinetic energy of the photoelectron and the stopping potential. Does it make sense for you, the first line? Come on, read it back. Okay, what they said? If frequency or wavelength of the radiation is kept constant, no change to the frequency. Okay, the light shine, we never change the frequency. Red light means always red light. Okay. Increasing the intensity of the radiation does not change the maximum kinetic energy. Do you agree? Explain, right? Intensity is does not change the maximum kinetic energy, right? So from the what formula? HF equals to work function plus EK max. EK max. Okay. The EK max is affected by what? EK max is affected by EK max actually HF minus the work function is the EK max, right? So EK kinetic energy is only affected by what? It's only affected by the frequency. It's only affected by frequency. It's not affected by intensity. Okay, not affected by intensity. Intensity doesn't affect the kinetic energy. Okay, why intensity doesn't affect kinetic energy? Intensity doesn't increase the energy of a photon. Okay, intensity doesn't increase the energy of a photon. But then intensity does what? What intensity does? Intensity only increase the number of photons. It only increase the number of photons. It doesn't increase the energy in one photon, right? What is intensity formula? I equals to intensity is what? Power over area. Power is what? Energy over area time. Energy is what? NHF over AT, right? So intensity as long as the frequency constant. So intensity doesn't change the energy in one photon. It only change the N over T. See, you change the N over T. You raise the intensity, no change in frequency. N over T rises. What is N over T? Number of photons per second rises. Okay, yeah, that's the first idea. Hope you understand. Okay, look at the second paragraph. Increasing the light intensity simply increases the number of photons following the unit area in unit time. Makes sense, right? So yeah, NOT. Increasing the intensity, it increase the number of photons per unit area, per unit time. Okay, this results in an increase in the emission of photoelectron. Yeah, intensity rises means N over T, the number of photons per second per area strikes the surface rises. So therefore, current rises. The photocurrent rises. The photocurrent rises. So remember, photocurrent is directly proportional to intensity. Increase intensity, number of photons per second rises. Photocurrent rises. Okay, the current detected by the micro emitter outside rises. Okay. Yeah. So this is our increased emission photocurrent. The incident photon still imparted the same amount of HF to every electron. Yeah. So intensity rises the photocurrent, but not the maximum kinetic energy. Frequency rises the kinetic energy. Okay. And the stopping potential. Okay, so that's the conclusion, stopping potential. Increasing the frequency. So remember, look at this diagram here. Look at this diagram. Stopping potential, frequency. Okay, so this shows different metal as a different threshold frequency. Okay, next. The third line is if the intensity of radiation is kept constant, but frequency is increased. There is a mistake here. The I we know is NHF over NT, sorry, AT. Okay. The intensity of radiation kept constant. I kept constant. F is increased. F is increased. Okay. F is increased. So what happened to the photocurrent? We actually not about photocurrent law. Instead of we are talking about a photocurrent. Okay. Cancel this idea. Not about photocurrent. Can you tell what will happen to the number of electron? What happened to the number of electron? Because in exam they'll ask more to number of. What happened to the number of electron released per second? What happened? Constant, increases or decreases from this formula? Anybody? The intensity is constant. The intensity is kept constant. What happened to the number of electron per second released from the metal surface? So intensity is constant, frequency is raised. If frequency raised, what happened to the N over T? When frequency rise, what happened to the N over T? N over T decreases, right? N over T decreases. That means the number of photons strikes the surface decreases. So the number of electron released the surface decreases. Okay. So you say but the frequency F is increased, the number of electron per second decreases. Okay, decreases. Okay. No need to go for photocurrent here. This is a little controversial, this part, actually. Okay. So yeah, take down this. So increasing the frequency increases the kinetic energy. Yeah, rise the frequency, kinetic energy rises, stopping potential rises. Okay. Any questions, guys, from here? So conclusion is what? Conclusion is you want to rise the EK, rise frequency. Okay. You want to rise the photocurrent. You want to rise the photocurrent. Okay. Photocurrent. You want to rise the photocurrent. You want to rise the number of photon per second. Rise the intensity. Okay. If you rise intensity, never change. Frequency raised. Okay, guys, come on. I need your input. Intensity never change, kept constant. Frequency raised. What happened to EK? What happened to N over T? Come on, give me answer. When
EK increases.
EK increases. EK increases. Yeah, good. Then N over T. Anybody? EK increases. What happened to N over T? So what formula in your mind? Intensity is NHF over AT, right? So no change to the intensity, but frequency rises. What happened to the NOT? The number of electron released from the metal surface. NOT can say, actually NOT is the number of photons strikes the surface. Is the same as number of electron released from the metal surface. So intensity never change, but frequency rises, EK rises for sure. What happened to NOT? NOT decreases, right? NOT decreases. Okay, all from this formula. Okay, let me ask you further. Frequency unchanged, intensity raised. Okay. I don't want to do, yeah. I just go to the difficult one. I don't want to use this. I use this. Intensity decreased, at the same time frequency rised. Intensity decreased, frequency rised. What happened to EK? What happened to NOT? What's up, me the answer? Guys, come on. This is important. Or you can tell me in the class itself. Anybody?
EK increases.
EK increases. NOT. EK is just checking the frequency. NOT?
NOT, no change.
NOT, no change. Yeah. NOT, no change. NHF over 80, right? So make the NOT as a subject. NOT as a subject, so it's going to be IA over HF, right? So frequency gets smaller. Intensity gets smaller. Frequency increased. So what happened to the NOT? Smaller, right? Get smaller, right? The numerator get small. The denominator gets small. Numerator gets small. Denominator increases. So the total value become even smaller, right? So NOT is get smaller. Okay, NOT gets smaller. So yeah, whenever they talk about I and F, the formula you must rely on is I equals to NHF over 80. Okay, N is the number of photons, H is the Planck constant, F is the frequency, A is the surface area, T is the time. Okay, so use this. But frequency, kinetic energy, very easy. You just check the frequency. Frequency go up, EK go up. Okay, so temporarily, let's we test this knowledge. Okay, well, we go to the one pass here. Okay. This one question. Okay. So this is one pass here actually. Immediately we go there. Okay, look at this question. First is explain what is meant by photon. You know, like last time for alternating current, what is meant by RMS value? The same famous, like RMS is famous in AC, so here going to be photon. Every time the question starts, they're going to ask what is meant by photon. It's a packet of energy of an EM radiation dependent to frequency. You can write the E equals to HF if you want. Okay. Next, the photoelectric effect provides evidence for the particulate nature of the electromagnetic radiation. Particulate nature means it's like a particle, like a package. State 3 experiment observation that support this conclusion. 3 experimental observation. So what is that? The release of electron is instantaneous. The existence of threshold frequency to release an electron. Okay. Third, you can say the kinetic energy of the electron independent of intensity. Yeah, kinetic energy of the electron is independent of intensity. So 3 factors. Okay, the focus I'm here is the part C. Okay, guys, come on. I give you 2 minutes. Okay, read the question. Tell me what do you think about the answer. C1 first. An EM radiation of the lambda and intensity I, when incident on a metal surface, causes an electron to be ejected per unit time, N over T. The maximum kinetic energy of the electron is Emax. Emax is the maximum kinetic energy. State and explain the effect, if any, on N and Emax. N is the number of electron per second. Emax, kinetic energy. What happened to the EK, Emax, and N? When the intensity is reduced to half, but the wavelength lambda is unchanged. You guys, come on. WhatsApp me or just tell me what you think. What will happen? What happened to N? What happened to Emax? Is it increases? Is it decreases? Or no change? Three options, right? First tell N. What happened to the N? Emax is easy. First Emax. What happened to the Emax? Anybody?
No change.
Yeah, Emax increase, decrease, no change.
No change.
Unchanged, unchanged. So Emax unchanged. Yeah, good. Kinetic energy never changed because wavelength never changed. You see, they try to trick you. They give wavelength is actually linked to the frequency, right? Wavelength unchanged means frequency unchanged. So kinetic energy unchanged. Okay, good. Emax unchanged. How about N? The intensity is reduced. The intensity reduced. What happened to the number of electron per second?
Also reduced.
Also reduced. Yeah, both reduced. Yeah, sign is reduced. Emax unchanged. Okay, good. So those who got N reduced, Emax unchanged, good. Okay, this is not okay. This I can say okay. Part one. A little challenging one is part two. Come on, I'm really interested to part two. Give me the answer for part two. What happened to N? What happened to Emax? Increase, decrease, unchanged. 1 minute for you. Wavelength lambda is reduced, but the intensity is not changed. What happened to Emax? Emax is easy, right? The wavelength is reduced. Wavelength reduced means frequency has been raised. So frequency rise, energy of a photon rise. So Emax should rise, correct? Emax should be rise, getting greater. Because frequency increases, energy in a one photon increases, Emax increases. What happened to N? Actually, this is earlier labeled this as N over T. Actually, N over T they're asking for because N they label it as number of electron per second. So what happened to the N over T? Anybody? Increase, decrease, no change? Yes, I need your feedback. If you reply majority of you wrong, then I go explain again. If majority correct, then I feel okay. What happened to N?
Is it decrease?
So N decreases. The others getting N decreases. So what formula in your mind? So I equals to NHF over 80. NHF over 80. I'm getting answers too. Yeah, two of you say decreases. Decreases, right? Is it decreases? So on this formula, yeah. Intensity never change. Frequency is frequency increasing. Therefore, N over T must decrease. The number of electron strikes should decrease. This answer. Okay, good. So those who got these answers, so you got the idea. Okay. So in exam, give a reason why you say that. Emax increase. Why? You said frequency increase. Energy in one photon increases. N over T decreases. So you can put it. You can follow this. You can tell this formula. But if you tell this formula, you need to explain what is each alphabet represents. Okay. You just said when frequency rises, intensity kept constant. N over T decreases from this formula. Okay. Okay. So hope you got the idea. Okay, so let's continue. Okay, the last graph tells you that cesium, potassium, sodium plate has been used. Cesium graph was traced to the left, close to the y-axis. So what you can conclude about cesium and sodium, which has a greater work function, which has a greater bonding? Cesium or sodium? Which one? Of course, sodium has a greater bonding, right? The electron has a greater bonding. Why? Because the threshold frequency is very high. Higher the threshold frequency means because you know, right? HF equals to work function plus EK max. The work function is actually can be written as HF naught. HF naught, F naught is the threshold frequency. the minimum frequency required to release an electron, threshold frequency. So F naught is greater. Actually, the x-intercept is your threshold frequency. So sodium has a greater threshold frequency. Okay. So I already told you this. What is meant by threshold frequency is the minimum frequency. Be careful, the keyword, the minimum frequency required to emit a photoelectron from a metal surface. The electron must absorb a certain amount of energy. It's called work function is in the material can be defined as the minimum energy necessary to remove an electron. Okay, so now like one example. So you see, what is the maximum kinetic energy of photoelectron? Look at the question, look at the solution. Does it make sense for you? Now we are using the idea of Einstein to solve problem about photoelectric effect. So what is the maximum kinetic energy of photoelectron rejected from the magnesium when it is irradiated by a ultraviolet light of frequency of this? So what is the maximum kinetic energy? So we know the maximum kinetic energy is HF minus the work function. So HF, Planck constant, times the frequency of the ultraviolet light minus the work function. Work function is actually, work function is the HF naught, right? HF naught, H times the threshold frequency. Is it threshold frequency or work function straight away given in the bracket? The work function is given in the bracket. So 5.9 times 10 power negative 19. Yeah, so you get the K max, Ek max. Okay. So hope you got the idea. Let's see, move on. Stop me if you got any questions. Okay, we go to the another one. Okay, guys, come on, your turn. 1 minute for you, as usual. Try to figure out what formula, how are you going to go about. Not necessarily you need to calculate. Just have some rough idea. How do you do this question? A conductor has a threshold wavelength of 0.85 micrometer. Threshold wavelength, same as threshold frequency. Threshold wavelength. Threshold frequency is the minimum frequency required to release an electron. Threshold wavelength is actually the maximum wavelength of EM radiation required to release an electron. Right, maximum wavelength required to release electron. Okay, from threshold wavelength you can find threshold frequency. We calculate the threshold frequency. So how do you find threshold frequency for threshold wavelength? V equals to F lambda, right? V equals to F lambda. We can find the wavelength, right? V is speed of light, right? It's all EM radiation, so V is speed of light. So V equals to F naught lambda naught. So lambda naught, you can find the F naught. V is speed of light. Okay. Okay, next. Okay, look at the B. Okay, B, its work function in electron volt. Okay, when it comes to quantum physics, when dealing with the particle physics, particles, smaller than atom, the energy it possesses normally we use electron volts. So sometimes they ask in electron volts. So I believe in AS, do you learn about electron volts, right? How to convert? Okay, you should know how to convert joule from electron volt. The one still remembers electron volt to joule is easier. Electron volt to joule, you must just multiply by 1.6 times 10 to the power of negative 19, right? Electron volt to joule. So joule to electron volt, you just divide. So work function, how do you calculate? Work function is HF naught, right? HF naught. So H times F naught, whatever answer you got in A will be in joule. Then you divide by 1.6 times 10 to the power negative 19. Should give you answer in electron volt. Okay. See the maximum speed of the photoelectron emitted when the conductor is irradiated by blue light of wavelength 0.49 micrometer. Maximum speed. How do you find the maximum speed? So what formula should come to your mind? HF equals to work function plus EK max, right? EK max. If you find kinetic energy, you can find speed one, right? So we find the EK max first. Can you find EK max? Do you know HF? HF is what? Planck constant times which frequency? Frequency of the EM radiation source, right? But here they give wavelength of blue light. So blue light is the source, EM radiation. So of course, frequency not given, wavelength given. Still we can find, right? HF is HC over lambda, right? HC over lambda. C speed of light over the wavelength, get the energy. Work function, do you know? We know the B answer is a work function, right? You know the work function from the B. We can find the kinetic energy already. We can find kinetic energy. Once you know kinetic energy, half mv squared is the kinetic energy, right? So you can find the V. But do you know the mass? Do you know the mass? Maximum speed of the photoelectron. The kinetic energy of the electron, right? What mass you needed? Mass of the electron. Use mass of the electron. Go to the front page of the question paper. Find the elementary mass of the electron. Key in. You can find the speed. Right. Hope the idea, the method I told you, that's what you thought just now. So yeah, so this is the working, right? F naught just C over lambda naught. You get that frequency. Work functions HF naught. Okay. And 1 EV is this much, 1.6 times 10 to the power negative 19 joule. So whatever energy you got, divide by 1.6 times 10 to the power 19 joule, you got EV function. From the HF equals to work function half mv squared, we can find the V max. EK max means half mv max squared. V max squared. So we can find the V max. So this is the speed. Okay. Okay. Yeah. Yes, come on. Another one. I'm doing these examples for you so that you can really get the idea. Okay. Spend 2 minutes. Come on, 1 minute. Look at the question. Try to figure out the solution. The photoelectric experiment. A beam of light of wavelength 700 nanometer is incident on a metal. So this is the wavelength of the EM radiation shining at a wavelength of 700 nanometer. Incident on a metal. Stopping potential is negative 1.5 volt. Or this is your stopping potential. No current is obtained. Okay, calculate the work function of the metal. You want the work function. So HF equals to work function plus EK max, right? EK max. Okay. So work function is what? HF minus EK max. What do you get? Right. Okay, so you got the idea? So how to get it? So work function, how to get the work function? Sorry, the HF. Yeah, HF. HF, what do you get? HF, HC over lambda, right? C speed of light, lambda is 700 nanometer, right? But 700 nanometer, you have to change to meter. Make all change to SI. Minus EK max. EK max this case stopping potential given. So actually EK max is EV stopping potential, right? EV naught or EVS. So you put elementary charge times stopping potential. Here don't go and put negative 1.5. So negative become plus is wrong. Don't put just 1.5 only. 1.5 only. Okay, just 1.5. So you put 1.5 times the elementary charge will give you the work function. Yeah, right. This is the technique you heard. Remember, right? This is what you thought of, right? So HF work function is Kmax. Make the work function a subject. EVS. The EVS just put 1.5 to get the work function. Okay. Okay, good. So hope you got the idea. So go to the next one. This is the ultimate question. Okay. Okay, guys. Okay. So let's we go through together. So this is a graph obtained by Millikan, of course. I hate to get this graph, but so the maximum kinetic energy versus frequency graph plotted by Millikan. This is maximum kinetic energy, not stopping potential. So you should predict what gradient represents. What is the x-intercept represents? What is y-intercept represents? You have to analyze it. Okay. What is x-intercept represents? Is the threshold frequency. So in this case, the 1.5 times 10 to the power of, I don't know, I can't, 15 is your threshold frequency. Your y-intercept is actually, I have to check, you have to go for the HF equals to work function plus EK max, okay? So this graph is EK versus frequency, right? Yeah. So EK, I rearrange HF minus work function. So y equals to mx plus c. Yeah. So the y-intercept is your work function. So the negative 10 is we know is a work function. The y-x-intercept is the threshold frequency. The gradient is what? The gradient is your it's a Planck constant. It's a Planck constant for this case. Okay. Interpretation. Okay, good. Okay, go back to the first question. What do you think the answer? Okay, this is a good question I never asked before. Okay. Which aspect of the graph could not be explained with the wave model of light? Yeah. Which part of the graph the wave model unable to explain? Let me clear this. Which part of the graph it unable to explain? You know what are the things the wave theory unable to explain? The emission is instantaneous. The existence of threshold frequency to release the electron. Third, the kinetic energy of the electron is independent of intensity. Okay. The release of electron is independent of intensity. Yeah, 4 things. So which factor portrayed in this graph? I erase all. Which graph? Which tells that wave model unable to explain? Anybody? The threshold frequency, right? The threshold frequency. You see, below 1.5, no kinetic energy at all. The electron not even reach the wire, no current, no kinetic energy. No kinetic energy means no current, right? So no current has been detected before 1.5. Okay, this shows that there is a threshold frequency, existence of threshold frequency to release the electron. Okay, yeah. Another one factor is the graph itself. The maximum kinetic energy of the electron looks like proportional to or directly is proportional to the frequency. Frequency affects the kinetic energy. That's another factor. These are the 2 factors. Okay, wave theory unable to explain. Wave theory predicted that kinetic energy depend to intensity, not frequency. So that's the first answer. Okay, so the existence of threshold frequency or the maximum kinetic energy looks like is dependent to frequency. Okay. Okay, that's the first answer. Okay, look at B. State the threshold frequency and hence otherwise determine the work function. I already told you the threshold frequency from the graph formula interpretation. It should be the x-intercept. So 1.5 times 10 to the power of, is it 15? Sorry, 13. 1.5 times 10 to the power of 13 hertz will be the threshold frequency. So we can find the work function, right? So what is the work function? Work function is HF naught, right? HF naught, threshold frequency times the Planck constant. Get the work function. Okay, see, use the graph to calculate the value of Planck constant. Yeah, the gradient, right? So get the gradient. The gradient is the Planck constant for this case. But when you calculate gradient, be careful. You see, just don't take these two numbers only. Check the bracket got some values at 10 to the power of negative 19. So the x also make sure you get 10 to the power of 13 outside here. So divide properly. Make sure all SI unit. You get the Planck constant. Yeah. So that's up to C. Okay, D. What is the stopping potential when ultraviolet light of frequency this much radiated on this metal A? How do you find D? What is the stopping potential when the ultraviolet light frequency of 3 times 10 to the power of 15 hertz radiated on a metal A? So stopping potential. So HF equals to work function plus EK max. Okay. So where do you get stopping potential? The EK max we can convert to EV naught, right? The stopping potential. Can you find the stopping potential? Do you know other informations? HF, do you know? HF is the photon energy. Yeah, they already said ultraviolet frequency 3 times 10 to the power of 15 is radiated. So you know HF already. F is 3 times 10 to the power of 15. Okay, we got the photon energy. Work function, do you know? Work function. Yeah, work function is a C answer, right? C answer is a work function. Work function, we know. Elementary charge, you can get it from the front page of the question paper. So you can find the stopping potential. Yeah. Okay. Okay, so that's your D. That's your D. Okay, go back to the answer. Yeah, this is working, right? Your D, yeah. This is working just now. You can check. Okay, E. Using the same axis above, sketch a line to represent the variation of maximum kinetic energy with frequency for a metal with a larger work function. If larger work function means how the graph going to change? It's going to shift to the right or to the left? Shift to the right or to the left? Larger work function. Guys, I need your feedback. Larger work function means shift to the right.
To the right.
Shift to the right. Very good. Shift to the right. The graph just shift to the right without change the gradient. Don't change the gradient. Gradient still Planck constant, so don't change it. Okay, they're going to check it. Yeah, shift to the right. Okay, so that's all. Of course, this line, right? Metal A, metal B, greater work function. So you should have a greater threshold frequency. Shift to the right. Okay, so this is the explanation. Okay, class. So I think time's up. Next class we continue. Okay, so hope you got the idea. Okay, so go and watch the video back. This knowledge is something new, something very highly theoretical, but it's important. If you don't understand, once you understand, it's easy. Okay, easy mark, I can tell you that. So go and watch the video back. Go and read the notes to understand. Okay. Okay. Thanks. I stop here. So those who don't have question can leave.